Hello and welcome to the presentation. In this presentation, I'll be giving a very brief overview of the problem of motion planning for multiple autonomous vehicles. So basically we know that technology is coming, future is changing, and what was once a dream is coming true. Soon we'll not have to drive our vehicles, they'll drive themselves. Government says it's safe and therefore better. They are aiming at reducing the road accidents. We feel that comfort is a real good factor. Nobody wants to do something as boring as driving. From the point of software, the software architecture, which is the main brain of these vehicles, is exactly what you should be expecting in a mobile robot, except for that everything has been mapped from a general robotics into a road and very traffic kind of scenario. We'll be basically looking at this thing, which is called as the problem of planning, which tells the vehicles how to move, what to do, what not to do, and all these things. This would be the focus of the entire research. So fundamentally, the research is broken down into two very related concepts. One is called as the problem of trajectory generation, which basically tells the vehicles how to move on a road, how to avoid other obstacles, other vehicles. And the other would be where the entire transportation system would be dealt with at large, which will say how the traffic light should operate, how should traffic be organized, how should it be managed, how the lanes change should take place, and all these things. So when it comes to the first paradigm, or the very first part of the problem, which is trajectory generation, what the problem says is, suppose we have a road like this, which obviously will have some static obstacles, which may be a vehicle broken down, a tree fallen, something suddenly came in front and stopped working. All these things, there will be some static obstacles, and there would be some vehicles out here. So let's say there's a vehicle out here, there's a vehicle out here, there is a vehicle out here. Say this is moving like this is moving like this is moving like this. The problem says how should the traffic operate. In fact, we can take this very particular instance as an example and try to predict, try to deliberate over how should it move. This, if maybe it's a very slow moving vehicle, it's a very socially unimportant vehicle, it waits here, this vehicle goes completes its trajectory like this vehicle goes completes its trajectory like this or like this vehicle goes in after all the both these vehicles and completes its journey like this. Or there can be multiple other option. Let's say the second option can be that this vehicle comes in like this, simultaneously this vehicle comes in like this, they'll both lie parallel out here while this is either waiting, or let's say this has already crossed in like this, or this has crossed in like this if the road was wide enough. So there are infinite possibilities. We need to find out the best possibility which appears to be, and obviously the vehicles may know about each other's plan if they are with some kind of communication facility, if they can talk to each other, else they might just have to guess. So the problem of trajectory generation is how to basically solve this kind of problem. Currently there are obviously two kinds of traffics which are operational around in the world. One is this kind of traffic, nicely organized within lanes. In fact, for a person to drive like this in between lane, it's not allowed. So all you have to do is to follow the vehicle in front, and if you've got space you can obviously make a lane change either left or right. And this kind of a very chaotic traffic, anybody is driving anywhere, anybody can move anywhere he likes, he can as long as it doesn't cause an accident, there's no concept of lane, everything is allowed. This, by the way, is Indian traffic, very chaotic. So our focus would be only this kind of traffic, as would be apparent from the previous slide, while most, if not the entire research is for this kind of organized traffic. This is what we study. And why do we study that? Or more importantly, why do countries like India follow unorganized traffic and not make it compulsory for vehicles to drive strictly within lanes? Well, it so happens that if we take the second picture and we deeply analyze it, what is happening in a road there are multiple vehicles of multiple sizes. They are all occupying the road. So let's say this was a motorcycle, this was some three-wheeler auto rickshaw, this was a big truck, there was a car behind. If we convert this traffic into an organized traffic, they might be I mean, this road might only be allowed having two lanes, one per side. So first motorcycle will have to drive like this, second motorcycle or this three-wheeler will have to drive like this. Now there's clearly a scope to fit in one more vehicle out of the available space. But since we've restricted the traffic to within lanes only, the bandwidth, as it is called, the maximum number of vehicles allowed, can never exceed 2. So this type of traffic is better when the vehicles vary a lot in sizes, and that's what you can see from the picture behind, that the number of vehicles were clearly very large as compared to this. Here only 3 vehicles, or let's say including this 4, was moving in very broad road, and here got those how many vehicles are moving out over here. In fact, they cannot be even counted here. So this kind, when vehicles vary a lot in their sizes, then the unorganized traffic starts getting better. And similarly, what unorganized traffic can do, like this vehicle can, if it finds sufficient space, it can overtake. And therefore, if vehicles vary a lot in their speeds, where overtaking is completely necessary, you don't want to follow a bicycle or a manually driven vehicle. It'll take a very long time. You want to overtake it as soon as possible, as and when possible. So unorganized traffic caters to the need that whenever separation is available, you can basically overtake. And therefore there comes a major point that when the vehicles do not vary much in size, when they do not vary much in speeds, when they are very much alike in nature, as in the American, the European, and so many countries the traffic exists, organized traffic is always better. If the vehicles vary too much, the unorganized traffic is better, and we've got a very nice example. In many states in US, motorists can drive in between lanes. So that's when you increase the size diversity, the diversity in the width of the vehicles, it starts taking unorganized formats. Similarly, if emergency vehicles come, which are vehicles of extreme importance, fire brigade, ambulance, people start taking unorganized traffic. They start defining speed lanes only to allow these vehicles to pass through. So as you increase diversity, traffic migrates from this to this, and that is what might happen in the future. People might discover autonomous vehicles which can do everything. So application specialists might make big vehicles, small vehicles, high speed vehicles, slow speed vehicles, depending upon the computational requirements and task requirements and all. And it currently organized traffic might, if diversity enters, might become unorganized in nature, which is of course thinking much into the future. Now, specifically coming into the problem of planning. Planning is a very broad problem that can be seen at multiple levels, at multiple hierarchies. I'll briefly take it through. Suppose you've got a pizza delivery system. It needs to visit 5 houses, so the strategic level decides on what order and then what procedure should those 5 houses be taken into account. So there's some strategic level which planning which depends entirely on the task in hand, on the specific application in hand. The more important is the route planning, which every city has some kind of a road network graph. There will be important roads, small roads, big roads. So the sub-strategic level will decide whether do I go like this, or do I go like this, or do I take in this route. They may have different level of congestions, different widths, whatever. So it basically tells me which route to select. The trajectory generation, of course, as we've seen, if there is one specific road like this, say this road, there will be multiple vehicles out here, there will be multiple obstacles out here. It decides how this vehicle moves, which trajectory do they take. Again, the trajectory will be different from normal road scenario, which is exactly this scenario. If it's kind of merging scenario or an intersection where multiple roads meet, situation changes, planning changes. For blockages where no vehicle can move, where the road is completely blocked, then some different primitives hold. In parking scenario where you need which is valid when you get into the road, you'll of course take your car outside from some parking zone, and then after you've completed repark at some parking zone, or it might be your house. So start and end condition, they are very different from the normal route planning. All these planning are different. In this specific research, what I would only be focusing upon is the normal route planning, which is this planning. Will not take up anything else. And we know that when we've got such kind of different level of hierarchies of planning, we always need a middle tier planning. And what its basic job is, situations will change with time, plan will have to be reformulated. Maybe a vehicle is going from a parking zone entering a normal road, so for some time this has to be called, for some other time the normal route planner has to be called. It has to detect whether there is a blockage. On detecting blockage, it has to act differently, or maybe call in different set of algorithms. The entire road cannot be taken up at one instance. So this kind of handling between one tier to the other tier is handled by the middle tier, and towards the end vehicle runs by some very specific control signals depending upon the motors, depending upon the torques. Those are generated by a low level control algorithm. Our focus will be only the trajectory generation here and the normal roads in this specific kind of trajectory generation. Now planning, as we have just discussed, we'll basically be designing a number of algorithms which broadly will be of two types. The first algorithms will say, see, there is a road like this, there is a vehicle out on this road which we are planning, whose plan we are trying to formulate. The vision of this vehicle being planned will be restricted. So let's say it can sense anything within this range. So if there's an obstacle out here, or if there's another vehicle out here, or there's another vehicle out here, it can sense. What continual planning will do is that, sensing all these things, the obstacles, the vehicles, everything, it will decide a unit move of this vehicle. So let's say immediately, how does it move? How does it change its speed? How does it change its steering? Will only be considered with one unit move. Maybe this vehicle, in order to make this unit move, it constructs in some small trajectory. Maybe it even constructs a longer trajectory. At the next time instance, when the vehicle reaches a different positions, based on whatever the output and based on whatever the planning algorithm did, at the next time instance, say the position would be something like this. The vehicle has moved like this. It senses in all these obstacles out here in its sensing range, and now we'll make a fresh start. We'll decide what the planning algorithm should do, whether it should turn like this, whether it should turn like this. So we'll plan as the vehicle moves. The trajectory, if used in the previous time step, can be carried forward. It may not be carried forward. The new trajectory may be generated, but the vehicle will plan as the vehicle moves, and the difference would be clear when I take up the other aspect of it, which is called as the per segment planning, which is another type of algorithms that we would be seeing. So let us say that we again have in some kind of road out over here. So let's say this is the road that I have out here. The vehicle is again out over here. We'll say that the vehicle can sense all the obstacles within some segment, say out over here. In this range, it can sense all the obstacles and other vehicles. So there might be an obstacle here, there might be an obstacle over here, there might be some vehicle out over here, based on which the algorithm will generate in a trajectory. Say it generates in a trajectory like this. The vehicle would obviously move as per this trajectory, but here we'll not replan the trajectory as it moves in the next time step. We will not again recompute the trajectory. Rather, what we'll do is that we'll trace out exactly this trajectory. So when the vehicle is here, we trace this trajectory. When the vehicle comes here, we trace this trajectory. We are using the same trajectory at every time instance till the vehicle moves out over here. And from here, when the vehicle is here, we'll basically use the same algorithm to calculate a new trajectory, say like this, or like this. Now, of course, the approach that I just presented, which is per segment planning, where we where we plan the trajectory of a vehicle. When it reaches the end of the segment, we again replan. It sounds very nice when we see these kinds of scenarios, these kinds of maps. In reality, there might be a small problem. The vehicle was here, we saw all these obstacles and other vehicles, we computed this trajectory, and the vehicle moves here. But unfortunately, what happened is there might be an obstacle out here. In case there is an obstacle out here, now the vehicle is standing here. It can neither turn right and avoid the obstacle, nor it can turn left. So it's basically stuck. The problem was that here I did not know about this obstacle, and now that I know, there's nothing that I can do about it. And of course, the problem can be solved with a very simple change in the basic algorithm. My basic algorithm would of course remain the same. I make in a very small change that in place of dividing these segments, saying that the segment number 1 is here, segment number 2 is here, I make the segments overlapping in nature. So by making these segments overlapping in nature, what do? I say, let this be the other segment. I say this is segment number 1. This is segment number 2, and this is segment number 3. 1 and 2 are overlapping, and 2 and 3 are overlapping. Now what happens? Again, the same trajectory is considered because the trajectory is planned for the entire segment. So for this entire segment, I planned the same trajectory. It goes here. But when the vehicle reaches this point, segment 2 starts. Segment 2 starts means it replans using the vision information for this entire segment. Using the vision information for this entire segment means that this red obstacle, it can now see this red obstacle way from distance, and now it can see that turning like this would be a much better option rather than going and dashing through the obstacle. So by a very simple change, by making the segments overlapping in nature, I can solve this problem that it will not come very close to the obstacle. Of course, the actual research will not make much reference to this kind of problem, but it's a very practical kind of problem where we do not want to go blindly by the planned trajectory of a segment. We want to stop way ahead so that any new obstacle at the distance can be sensed. And the important part, there are fundamentally two kind of modeling that we would be using. One is when all the vehicles are have some kind of communication with each other, so they can basically talk to each other, and the other would be that when the vehicles cannot talk to each other. Now, this has got a very specific practical relevance. Some people say that when technology comes in, the human driving would become very dangerous. Whereas when you are driving by an autonomous vehicle, you can always drive at high speed. The autonomous vehicles don't get fatigued. They have got very good vision. They have very fast reflexes. So they can drive at very fast speed, and the speed limits would be raised. It will get more dangerous for the human drivers, and people will ultimately debate for the human drivers to get eliminated. Nobody might, the technology might anyways make human driving obsolete. The other modeling scenario says that, of course, that the human drivers would still be there. They would be manual vehicles, or they would be very different vehicles who cannot talk to each other using the same protocol. Now, communication helps in multiple things. A vehicle can help the other vehicle locate it, can tell in advance the obstacles ahead. We'll only be using communication for this kind of thing, which is for the specific problem of planning. Our assumption of communication only in some of the algorithms, not all of the algorithms, would be restricted to the problem of planning only. Now, it would be a valid question that why are we assuming communication at all when you've got algorithms that can work without communication? if you got both kind of algorithms, ones that work with communication and ones that work without communication, it might be better to only use the algorithms which work without communication. Now, even in practical life, it so happens that you want to do something, and you do not only and you do not do that because you kind of predict that the other person might do something contrary, or he might you I cannot take something what I you want to take something, but you do not take, the other person might take it. So you have to consider all the possibilities that the other person might do, and as a result maybe you do not do something which was good for you because the other person might benefit from it, and he does not want it. The better way, of course, would have been that if you could both could talk to each other and decide what to do. So when we have an extra element of communication, if available, there's a possibility of making the overall optimal plan, or overall near optimal plan, overall better plan. With communication, we might miss out on something which we could have communicated better. So that's why we've kept both possibilities. Whatever the future be, the algorithm can be presented either with the assumption of communication or without the assumption of communication. And one of the last things that I would be taking up in this introduction is the coordinate axis system. Whenever you work with robotics, there are so many coordinate axis system. One is, of course, the conventional Cartesian coordinate axis system, which is always associated with the robotics, which is associated with the general world coordinate axis system. The other is called as the road coordinate axis system. So basically, a road is characterized by two boundaries. One is called as the boundary 1 and the other is called as the boundary 2. In all the algorithms that we present, this would be an additional coordinate axis system apart from this one. Here the x-axis would be a very funny axis. It will be this axis. So it's basically for a curved road, it's curved as the second boundary. Maybe most of the roads are straight, but not all. Many times in highways and in flyovers, the roads are curved, so this axis may be curved. The second axis which we would take is kind of this axis. So this is my x-axis and this is my y-axis. The only catch here is that any point, let's say any general point, of course this would be, I'll change the pointer. Of course, when for this point, this will be its x coordinate system. To differentiate between the two, let me call that as the x dash coordinate system. So this will be its x dash coordinate axis system. This point will be represented as x dash, and in place of using this as the y-axis value, I simply take it as a ratio. So let RL be the road length and let A be this distance. My y dash value will be A by RL, which is a ratio, which is again something very funny. Now, taking in a curved axis and a perpendicular y dash axis was simple, was obvious, because if I take in such an axis system, I can very easily generate points inside the road. Say I want to generate in a point which is strictly inside the road. So many of our systems are sampling based, which have this kind of problem. You need to take in a random point inside roads. I know this entire length of the segment, so I'll generate a random number between 0 to delta and between 0 to 1. And it'll be guaranteed that my point will be lies inside the road, which is not something which would have happened had I considered this kind of coordinate axis system, where I do know where a random point can be this, a random point can be this. So that's why I've taken a very funny axis which has a curved x-axis and a perpendicular y-axis. In general, this would be called as the longitudinal axis and the lateral axis. The y-axis, the lateral axis, the x-axis, the longitudinal axis, or the x-axis, the longitudinal axis more specifically. The reason why I have not taken this as A, rather I have taken it as A by RL, or a ratio. One, it bounds the point between 0 to 1, which is good. The second reason is that many times what may happen, that the road may not be of equal width. I have to take that possibilities. I'm taking very arbitrary kind of scenarios as well. So I have to take the scenario where the road is, let's say, generally broadens. This is the kind of road that I have, and that's practical. I mean, many times the road at one region cannot be broadened, but towards the later it just broadens. Now, how vehicles would drive like this is like this. They won't might not go like this, but rather they may go like this. So in general, we keep the relative position same, and from the same philosophy, the motivation of the ratio comes in. On such kind of roads, if you would like to, in fact, if there's a beam of vehicles, that is how they would travel. If there's a beam of vehicles, they would all drive very close to each other out here. There's vehicle 1, vehicle 2, vehicle 3. They'll follow very close to each other here. As the road broadens, they'll spread out. So if I use this kind of axis system, I see the relative position is not changing. The ratio of the three vehicles with respect to the road is not changing, and therefore this factor would be constant. The ratio would be constant, and therefore, again, it's a very small difference. In general, it does not make much of a difference, but that is what I've considering these as valid possibilities. That is what I've taken, that the x-axis is taken as the curved axis out here for curved roads, and the y-axis is firstly taken perpendicular to the x-axis and secondly as a ratio. The very other problem that we would be solving is that of the entire transportation system. So we'll be dealing with everything that we can do, with all that we can do under various kinds of assumptions. I'll be taking very specific problems depending upon the modeling scenario. So like this, you've got the map of where I study. It's the map of the town of Reading, United Kingdom. And we would be basically seeing that what all can we do if we've got such a map. How can we manage traffic? There'll be numerous vehicles here, there'll be numerous vehicles here, there'll be numerous vehicles here, there'll be traffic lights. How do we operate the traffic lights out here? How do we manage the flow of the vehicles out here? How do we manage the flow of vehicles out here? When lane change should be allowed, when lane change should not be allowed. And to give you some flavor, these are the three specifics which will be taken. The first is dynamic traffic management, where we'll assume that not all, most of the vehicles are autonomous. They have some kind of communication, or they are human driven, but the human can be given some kind of driving instructions. And then we'll see that what magic can we create. I mean, we can seriously create a magic. We'll see what magic can we create, how the entire traffic behaves very different, how it behaves really well for overall management. But of course, most vehicles being autonomous is not a good assumption. So in the second problem, what we would be dealing with, we'll be solving the problem of congestion, and we'll be solving it without the assumption of most vehicles being autonomous, but with the assumption of the traffic being non-recurrent, which means that the trends do not repeat with time. What happens today might be very different from what happens tomorrow, might be very different from what happened a week before. Traffic trends keep changing with time, and that's why most of the traffic jams happen. You do not expect a traffic jam to happen, it never happened, and then still it happens. We'll be looking at the city kind of scenario, which is a highly connected, too many roads, multiple alternatives to reach your destination. Such kind of scenario, we'll be seeing what all can we do, how can we avoid congestion, which is a very difficult problem to solve. Next, we'll be taking up with recurrent traffic, where the trends do change with time, and we'll see how can this factor of trends changing with time be exploited to first compute a route, and secondly to compute the start time of your journey. So you have to cater to an appointment. You have appointment at a place you don't know, traffic you do not know about, but the system will calculate what is the best start time depending upon how much risk you can take of being a little late for the appointment. Depending on that, the system will give you the best start time, the latest start time, and the best route to take. And then we'll also later extend this approach to say that suppose you took the most prevention, still got late, then how can the transportation system assist you? You are running late. How can it assist you in catering to the appointment and actually do reaching appointment on time? What can we do at the transportation level? How can we make the overall transportation system being cooperative to people getting late? And from here you should be depending upon the platform in which you are watching the presentation, you should be redirected to some or many of the algorithms which will solve all the problems that have been highlighted so far. Thank you.